again. This is now not a drill, this is a real lecture. So, last time we discussed possible symmetries in a disordered system, and we built this table, which is the table of all symmetry classes. There are in total 10 of them, and they have these fancy names. And these 10 classes correspond to 10 types of symmetric spaces that were discovered approximately 100 years ago by Elie Cartan. And today we will continue this topic. We will extend this table. So it's only 10 classes. It cannot be extended downwards, but it can be extended to the right. And before doing this, I will erase this column with the names and replace it with a new column, which is the main one from my perspective, and it will be about the sigma model. So this column here are the symmetric spaces to which the scattering matrix, or the Hamiltonian, belongs, and next column will be the column for the Q matrix. And yeah, there will be no any derivation. I will just tell you the correct answer. So we have derived only one sigma model, which is the sigma model for the unitary class without any symmetries. And we found that the Q matrix belongs, actually this is the wrong one, belongs to the following symmetric space, which was U of 2n divided by twice un. And this is a different n. The small n here is the size of the Hamiltonian. Hamiltonian is a matrix of size n. This capital N is the number of replicas. It's a completely different space. Sigma model lives not in the real space, not where the Hamiltonian does, but in some complementary space, which is the space of replicas, and 2 is retarded advanced, which is also not where the Hamiltonian operates, rather where green functions are. So there is a one-to-one correspondence. Once you know the symmetry of the Hamiltonian, you also know all the soft modes, all the diffusons and couperons, as we discussed last time, which means you also can derive a sigma model, and it will have different spaces, different structure of these manifolds where it lives. And the more symmetries you have in the Hamiltonian, the more degrees of freedom you have in the sigma model. So your Q matrix should encounter for all possible diffusons and couperons. That's why each symmetry that you add to your Hamiltonian will expand the size of this manifold for the Q matrix, and it will at the same time reduce the size of the space for Hamiltonians. For example, I add time reversal symmetry, and my unitary class is reduced. Instead of any unitary matrix, now S takes fewer values. It's un divided by something. At the same time, the Q matrix, the space for the Q matrix, should expand. That's a good question. This is the orthogonal class. We didn't do this derivation, but I can just tell you the answer. The answer is like this. The Q matrix will belong to a similar space like here, but instead of unitary matrix will be a symplectic matrix. Spn times Spn. Yeah.
So do I understand correctly that means that we should have some other restriction? No, not Q square equal to 1?
Q square is still equals to 1. I will just explain now. So in the orthogonal class, orthogonal Q matrix is still a lambda matrix which is rotated by some matrix T, but this rotation matrix T now is not unitary, it's symplectic. And this is related to the fact that this matrix T actually rotates the original fermionic fields. So in unitary class, these fermionic fields were complex fields. We had phi and phi dagger, and they were rotated by unitary and unitary dagger. Now, when we have time reversal symmetry, this fermionic field will be a real field. So it should be rotated with preserving some real structure. That's why it's like orthogonal or symplectic, depending on whether you are in orthogonal or symplectic symmetry class. So actually, here, in the symplectic class, it's just the opposite. Here it will be orthogonal of 2n divided by twice orthogonal of n.
So the statement is that if one has a Hamiltonian with time reversal symmetry of positive sign for t squared, then after performing the Hubbard-Satonovich transformation, the saddle approximation gives you a manifold of that.
Yes.
As you move into that.
Yeah. I didn't show you this derivation specifically because there are a few tricky things there that I didn't want to bother you with some very technical details. But conceptually, you consider Hamiltonian which has a symmetry like it's a real matrix, a real operator, and it means that this four fermionic term that was decoupled by Hubbard-Satonovich has now some more complicated structure. And then to decouple it, you need a Q matrix which has a more complicated structure, which actually turns out to be the matrix of this form. Yeah.
For the unitary case, we have some space where Q is living, but when we have an additional symmetries, this space becomes smaller. So we should have like integration over zero mode in this functional integral. Is it true or?
Zero mode? What do you mean by zero mode?
I mean, like if what means that Q is living in smaller space than the general one. So
No, it's a bigger space. This space, this is the smallest one, and these two are bigger.
That's one thing which is, oh yeah, so like it's bigger in the sense of it's not just unitary transformations that keep it.
No, wait. That's
but also others.
maybe I should be more specific. Again, I didn't really want. That's not for the board, right? To be precise, I didn't want to do this, but for example, for symplectic class, actually what's happening here is 4n divided by twice 2n. That's a better way to do this. It's the same symmetric space, just the dimension is doubled, but actually it's larger than the original one. So originally you have unitary rotations which couple only electrons to electrons. Now here you will have orthogonal rotations, but which will couple not only rotate electrons into electrons, also electrons into holes. It's like this. You have the diffusion. Diffusion, we all remember what it is. It's a ladder with opposite arrows. And in a sense, this green function that you have up here, it's the correlator of psi and psi dagger, of wave function and this wave function. And the other one below is like this. It has psi dagger, psi pointing in the opposite direction. So your Q matrix is like a field that combines these two fields inside. Now, if you want to also include couperons in the Q matrix, you have two psis on one end and two psi daggers on the other. So you need a bigger Q matrix such that you can also have this type of elements. I understand this is still not clear, right? Let me give you a third explanation. We had psi dagger psi term, and then we did Hubbard-Stratonovich to decouple it, and we decoupled it like this. We replace one pair by the Q matrix. Now in the orthogonal or symplectic class, you can also interchange fields here, so you can write like psi dagger, psi, and decouple it this way, and replace this with a Q matrix. So you need a bigger Q matrix such that you can include both types of decoupling inside. But then, since these two psi's are actually the same field, this bigger Q matrix has an additional symmetry that it should be either orthogonal or symplectic, depending on the spin structure of these fields.
So here you technically, like in total, you have three channels, right? 3 ways to decouple.
Actually, only two. I mean,
Like you have the Hartree one.
that Hartree one we do not include in the signal. It's these fields, they also bear replica indices. It's IIJJ, sorry,
Oh yeah, right.
IJJI. So you should always decouple such that it's a matrix in the replica space, not a scalar. Again, these are all the technical details that I wanted to avoid, so you just should forget them right now and just the outcome. Q matrix lives in some symmetric space. There are only 10 of them possible, and the symmetry of this space is uniquely defined by the content of the modes of diffusons and couperons that you have in the sigma model, which is also uniquely defined by the symmetries of the Hamiltonian. So once you know the symmetry of the Hamiltonian, you immediately know which space this thing belongs to and which space the Q matrix belongs to. Yeah.
I have a little general question about this. So we started with having material which has some dimension and impurities like disorder.
Yeah.
And how in this setup we can see some properties that are shown here that are determining our class of topological material?
Well, first of all, it's not yet topological. It's just disordered. As I just said, these properties are determined by symmetries. So you can have a system which is disordered and which violates time reversal symmetry, or a system that preserves time reversal symmetry. And these two situations result in two different types of signal model and two different symmetry classes.
The K part is not disordered part of Hamiltonian, right?
Sorry?
The K part which gives us the symmetry is not.
No. Disorder should also obey the symmetry.
But all disordered parts satisfy the condition of the average and equal to the delta function.
Yeah, but this is not the symmetry.
You always incorporate disorder with replica.
For example, you can have
Interacting model.
random potential, which is random, and which is a potential in the sense that it's some real function. V of r is a real function of space, so it also obeys time reversal symmetry. Or you can have some complex random potential which will violate time reversal symmetry. Well, potential cannot be complex, but it can be random magnetic field, for example. Magnetic field, or magnetic impurities that have embedded magnetic moment in them. And then they will violate time reversal symmetry, and you will have a different symmetry class.
Is there like any review articles that have
Yes, there are a few of them, and I believe I can mention one, which is, but it's not, despite the fact that they are review articles, it doesn't mean they're very accessible to a non-expert. So one such article is by two gentlemen with the names Evers and Mirlin. It's in the Reviews of Modern Physics. I believe the year is 2008, and the title is Anderson Transitions. under some transitions. So they have all these types of tables in all possible ways. This is just one article. There are others. I'm just this one is the most comprehensive. It doesn't have only this kind of tables. They also explain in detail for each class what type of properties you can observe, like localization and related stuff. Okay, so let's continue. There are three chiral classes which we didn't discuss in much detail. So Hamiltonian has chiral symmetry. It's a block of diagonal matrix, and the corresponding sigma model is for this chiral unitary. It's just unitary UN, nothing else. For these two, I believe it's the same as here. Yeah. So chiral symplectic must be UN divided by SP, and sorry, it's chiral orthogonal. Chiral symplectic is UN divided by ON. Yeah. And the last four, we have these four states here, and we have the same for here in some other different order. It's O2n divided by UN, and this is SPN divided by UN, and then the last two are just ON and this PN. So once again, there are only 10 types of symmetric spaces in nature. This is almost the exact statement. And the Hamiltonians belong, depending on the symmetry, belong to one of them. And the Q matrix in the sigma model also, depending on the same symmetry, belongs to one of them, but to a different one. There, in some sense, there is a duality between these two things.
This doesn't include symmetries which are, for example, represented by commutators.
No, they're only anti-unitary symmetries, yes. The symmetries which are commutators, as I explained last time, mean that you can diagonalize them and you can reduce your Hamiltonian to a smaller one.
And they just are independent.
Yeah, then study just independent things. So to finish this topic, if you let me, I will erase this reference because I will add the one last column to this table. And this is weak localization correction, which we computed in all possible classes, delta sigma. So in the orthogonal class, it's the second line here, we found this is the simplest one. We have seen a weak localization correction, which is negative. So the conductivity is, there is a quantum correction, which is minus e squared over 2 pi squared h, logarithm of something. It's negative. So I will put minus here. Minus means negative. And for symplectic class, the correction is positive. And for, I can even write the exact number. So it's, if you like, this whole column is a beta function. So beta function, which arises when we renormalize the sigma model, is universal. In each class, it's different. And in the orthogonal class, it starts with minus 1 over g, and symplectic with plus 1 over g. And in the unitary, it is 0, because there is no first order correction, but there is a second one. So there is some minus 1 over sigma correction that is negative, but in the next order, in the leading order, it is 0. And as I said, the same can be done in all other classes, and the nice thing is that is this universality. Once we know the symmetry, we know which class we are in, we know immediately the answer, what the weak localization correction should be. For example, in the chiral unitary class, we did not derive it. I'm just telling you. It is exactly 0 to all orders. Beta function is identically 0. For chiral orthogonal class, it's identically 0. And for the chiral symplectic class, it is identically 0. This is a special feature of chiral classes. In chiral classes, there are no weak localization corrections to conductivity. We will discuss this later today.
Yeah, but still, like if you have a, like that's in, it isn't like when you take the scaling hypothesis, right? In one limit, like in the limit of large conductivity.
Yeah, this is what you do.
It scales towards dimension -2. But
Yeah.
in the other limit of a small system, it should tend towards, I think, logarithm of.
Right. And then you can calculate.
It's always 0, then it will never.
Always 0 means it is 0 in all orders. If you expand it in powers of inverse g, you will get 0, 0, 0, 0, 0, which means it's non-perturbative. So it can be like exponent of minus g.
That makes sense. So you can't get anywhere with perturbation theory.
Yeah, the perturbation theory does not provide any corrections, which doesn't mean they do not exist. It's just perturbatively 0. And for the last 4, it's like this. It's plus, minus, plus, minus. So in these classes, we do have weak localization, more or less similar to what we had in orthogonal and symplectic with these signs. Okay, so we have so far discussed in detail these 3 classes. The unitary class in more details. We have derived the sigma model. We have found this space here. We see the action. We know how to renormalize it. We have derived this -1 over sigma thing. For orthogonal and symplectic class, we did not derive the sigma model, but still we computed weak localization corrections. And we so far did nothing in any of these other classes. So the first topic today, after finishing this table, is the explanation why we have 0 in these 3 classes here. And this statement has a name. I don't know how to speed up this thing. It didn't behave like that before.
You can create a new page and they will switch much faster.
Or you mean it's just that I have a very large page here, yeah? Okay. That's nice. Because I thought I had to delete the older files, but okay, yeah. So the topic or the statement goes with the name Gade and Wegner. These are two people. Gade-Wegner theorem.
This isn't Wagner, it's Wegner.
Wegner, yeah, it's Wegner. It's Franz Wegner and Renate Gade. So Franz Wegner is the German professor. I believe he is now retired. He's quite relatively old guy. Renate Gade is his student actually, and they found this theorem in the year 1990, more or less, 35 years ago. And the theorem is exactly what I just said. There are no perturbative corrections to conductivity, to sigma, in chiral metals, in metals which have chiral symmetry. Or more precisely, in the disordered metals of one of these three chiral symmetry classes. This is the statement of the theorem. And to prove this theorem, these two people have used nonlinear sigma model. That's why we will also use the nonlinear sigma model. It's very easy. I mean, the proof is very simple. As long as I find the page where I have written it. Yeah. No. Yeah. So, chiral symmetry, I just remind you. Chiral symmetry, what we call CT, the combination of C and T, means that the Hamiltonian is anti-commuting with a matrix sigma, where sigma can be brought by a proper choice of basis to this form, 1 minus 1, which also means that the Hamiltonian in this basis is an off-diagonal matrix, H, H diagonal. This is true for all chiral classes, and the distinction between unitary orthogonal symplectic is whether this small h is complex, real, or real whatever, quaternion.
The sigma is not conductivity, so maybe like underline Z or something.
Sorry?
Maybe underline it.
This sigma?
Like one
That's it. Oh, sorry.
maybe sigma Z and sigma 3.
Conductivity. Okay, so what is special about chiral classes? Except that the Hamiltonian is like this. We discussed it also last time, that in every class there is a diffusion mode, and when we have a chiral symmetry, we can apply this chiral symmetry to one of the functions, and we have a diffusion, right? Which is retarded advance diffusion. We apply this CT symmetry, and what we get? So this line didn't change. We get RR Cooperon. We get the mode which has two retarded functions which point in the same direction. This is retarded Cooperon.
Just to make sure, so when you say apply the symmetry,
To only second line.
I mean, you're not actually applying it, you're just saying that, okay, my bottom line actually equals to
Yeah.
our line. So this is not like application, this is just, we just say that this thing is equal to this thing, right?
Yes.
Okay, perfect, thank you.
Well, and for example, in chiral unitary class, these are the only two modes, there are no others. And the theorem is already correct. That's why it should be possible to see how it works with these two modes. And the first statement before we prove the theorem, the first statement is the following. There is something that didn't exist before, or there are, but rather than is, there are quantum corrections, but not to conductivity, corrections to density of states. Does anybody know how to calculate the density of states with green functions?
Imaginary part of
Yeah.
target function.
Density of states is a function of energy. It's in all previous cases that we studied, it was called nu. Right? The integral of momentum is nu, dic psi, nu is the density of states. So in all previous cases, nu was a constant. It was just a number. But in fact, it can depend on energy. When it depends on energy, I prefer to use a different letter, rho. And yeah, by definition, it's almost by definition, it's -1 over pi trace of retarded green function at given energy. Green function is a huge matrix. It's an operator. It can be traced.
And it's imaginary part.
Oh, I forgot. Yeah, right. Imaginary part. Trace of the imaginary part -1 over pi. Or you can also write it like this. Let's take retarded function and subtract the advanced function. Yeah, these two things are complex conjugate. So if we subtract, only the imaginary part remains. So it should be divided by 2 pi I, and probably still minus.
Yeah.
So we can draw a diagram.
That's only for real energies.
Yes, this is only for real energies. So there is a diagram for the retarded function. It looks very simple. It's a loop, a green function, which trace means we take it at coincident points. The point of origin is the same as the final point. And for example, this might be a retarded function. That's it. And now, in the chiral class, unlike it was in all other examples, we can have soft modes that are built only with retarded functions, which means that we can, so as usual, we add here impurities, and then we average them by connecting with some dashed lines. But this all was done before just using the self-consistent Born approximation. I mean, there are only self-energy diagrams. Now, once we are in the chiral class, we also can have a diagram like this. Yeah, this is the green function, which is retarded and which returns to the same point. And then we can insert a ladder here, and this ladder is retarded on both sides and has arrows in the same direction, so this is exactly the retarded Cooper. This was not possible in, say, in the unitary class.
Why? Because it's 0? Or?
No, because in the unitary class we don't have such a mode. Or, well, you still can draw it. It will be very small. I mean, we don't have such a mode. That means that this ladder doesn't have a singularity at small momentum and frequency.
Okay.
And here it does have, so this diagram will be much larger due to this singularity. And this, so this is like rho 0, the simple approximation, and this is a delta rho. This is the quantum correction. It's a quantum. It's not a classical correction. It's quantum. It's not. It is not included in the Born approximation, so it should be added separately.
Can you repeat this? How did we get this diagram?
We have all possible diagrams with dashed lines that intersect in any way they like. And originally, I argued that intersecting of these lines is introduces some small factors, therefore they should not be taken into account, and in the leading order, only non-intersecting diagrams are relevant, which means self-consistent Born approximation. And this self-consistent Born approximation actually produces constant density of states. We didn't do this calculation, but you can take the green function with 1 over tau, compute the density of states, it will be the same number as without any disorder. So disorder does not change the density of states. Now I'm saying, as we did with conductivity, let's add to this diagram a quantum correction, something which is small. And I say it is this diagram. Maybe I should have done it in 2 steps. I can draw the same diagram. It's the same diagram, like this. It's a fan-shaped diagram, but the fan is inserted in the, like that. I mean, all dashed lines intersect. And again, in the original case, in the unitary class or in the orthogonal class, when there is no chiral symmetry, this correction would be just very small. It's not even worth considering. In this class, this correction is not so small. It's a small correction. It's a quantum correction. But since we do have now in this class such a special soft mode, the integral in this loop will be logarithmic because we have this q squared in the denominator in the soft mode. It behaves as dq squared, actually plus 2e, but never mind. So there is some logarithmic. So this diagram has a logarithm inside. It has a small factor times a big logarithm. It's small factor because it's with crossings, but it's the same as it was for conductivity before. There was a conductivity without crossings that give us the Einstein relation, and then there was a quantum correction due to this type of diagram. So now in this class, when we have a chiral symmetry, exactly the same story happens not for conductivity, but for the density of states. It's a quantum correction. It is supposed to be small, but inside this loop we have some logarithmic integral, so it is not as small as it originally might seem. Yeah.
So will we see it explicitly?
See what?
The logarithmic divergence.
You take this and you integrate it over momentum, and it's logarithmically divergent.
Then I really want to compare this explicitly with what we had for unitary case, if it is possible. Because for unitary case we had nearly the same formula, right?
For diffusion, not for retarded Cooperon. Yeah.
Retarded Cooperon, we just didn't have this mode.
Yeah, it didn't exist in that case. In that case, only diffusion existed, which had exactly the same dependence, you're right, but it was built in a different form from the green functions.
Okay, I will ask that later.
Why is there a two?
Hmm?
Why is there a two?
Two where? Ah, you mean this? But because originally it was frequency. That's a good point. Let me explain it right here. So chiral symmetry, as I also explained last time, allows us to convert advanced function into retarded function, but it also changes the sign of energy. So if you take retarded function of energy and you apply chiral symmetry, you just multiply it with sigma on both sides, what you get is minus advanced function of minus energy, and probably also transposed.
Yeah, okay.
But doing trace doesn't matter.
Yeah, the trace doesn't matter. So in this so the frequency at this retarded Cooperon is the difference of energy of the upper and lower branch. And even if you take a diffusion which is at zero frequency, which has both equal energies here, one of them will flip sign. So what you can get here is twice the energy. And
Just a logarithmic singularity.
yeah,
Got it.
actually with I. And it will maybe minus 2I here. Doesn't matter, yeah.
Okay, like
So-
the
so-
two was what was weird.
Yeah, 2 is because you have E and minus E on the two lines.
Okay,
So we will not do this calculation. We will not calculate this diagram for a very simple reason. It's a simple diagram. It can be easily calculated. But we will not do this because actually it's not the only diagram that defines this correction. So to really calculate this correction, you need many more diagrams. And the better way to find this correction is from the sigma model. rather than from diagrams. It's just an illustration that there are quantum corrections to the density of states, because we now have this kind of mode.
Okay, I will try to keep it short. So, in principle, we would draw absolutely the same diagram for the unitary or orthogonal system,
Yes.
right? Okay, perfect.
Will be almost zero.
Almost zero, because there is no logarithmic correction. In both cases, the diagram is more or less integral over the green function.
Is more or less what?
Sorry, in both cases, it is like the same letter, right? But in unitary,
You mean it's the same density of states?
yes, I mean, formally it looks like the same, like RR Cooperon.
Yes.
But in unitary class, this RR Cooperon is extremely small.
Is very, 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 very small.
Why?
Because if you take two retarded functions,
Yes.
sit where it, and you compute not the whole Cooperon, just one step of this ladder, just this one step, you have the integral over all momenta, which I write nu d psi, of two green functions, which are both retarded. And retarded green function is epsilon minus psi plus I over 2 tau squared. And this is 0. Because you have the pole of the second order in psi that lies in only one half plane. You complete the contour in the other half plane and you get 0.
Okay, yes. And in case of chiral class,
You replace psi with this matrix,
okay, yeah, perfect.
which has chiral symmetry. And now you will have this matrix has, for a given momentum, has both positive and negative eigenvalues, and you will have poles on both sides in each function. Each function becomes a matrix. Now it's not a number, it's a 2 by 2 matrix at least.
Yes.
And you have one 2 by 2 matrix here, the other 2 by 2 matrix here. When you multiply them, you have a 4 by 4 matrix, and in some matrix elements, you will have a non-zero result. This is exactly the reason why we will not do this calculation, because I don't want to bother you with all these matrices, how they contract. And even if you do this, it will not be enough anyway.
Does it mean that now our retarded function have poles both in,
Yes.
and this is kind of not a retarded function?
And this is what?
This is then not retarded?
No, it is retarded, because retarded function, by definition, is a function that has singularities only in the lower half plane as a function of energy, singularities in energy.
Okay. Okay.
So we will
Yes,
have,
thank you.
it still has energy plus I over 2 tau,
So, but psi, which is...
but minus
yes.
some matrix like this.
Okay, yes, thank you.
So usually there's no restriction that in psi it should be only in one half plane. It just happens so for simple functions, and it doesn't happen like this for chiral systems. But as a function of energy, the pole is only for negative imaginary energy. Okay, that's a good point. Actually, I hope it's a little clearer now. So, what is the density of states, including all these quantum corrections? I will just show you the answer, and you will immediately realize why we don't do this calculation. So the answer, density of states, which includes all quantum corrections of the one loop order, only one loop order, not any further, is 1 divided by energy times exponent of minus some number here which I don't know, divided by sigma squared logarithm squared of energy. Just to make it proper dimension, it's energy times tau.
So this is like a pseudocode log.
And this is energy squared. Sorry? No, it's 1 over energy. But just to make it proper dimension, It's 1 over energy times tau and times nu in the numerator. So nu is that density of states that was before we included any quantum corrections. So these quantum corrections, they do not just change density of states a little bit, they change it very much. I mean, it looks energy as a function of concentration. Just imagine this is our spectrum where we add electrons one by one, we fill this state, and the Fermi energy grows. Fermi energy is the largest energy up to which we fill the spectrum. So we add electrons, 1, 2, 3, 4, 5 electrons. What happens to the Fermi energy? Fermi energy just stays at the first London level. So we fill this delta function one by one, we fill it here. As soon as it's filled, we have a jump, and then we fill the second London level. Then we have a jump, third London level. So these are London levels. E0, E1, E2, these are energies of the London levels. And if we somehow average out this ladder and draw the average line, its slope will be just mu. Because without any magnetic field, we add electrons and we fill with the energy grows according to the density of states. Now, these three plots are the only thing you have to see once. Now, what happens if I take a system in a strong, the third plot. I have many plots. Okay. Imagine the following thing. You would like to draw sigma xy or conductivity, this thing, as a function of chemical potential. If chemical potential is between these two levels, it means we have some fixed number of levels filled, and we have some fixed sigma xy. Then, when our chemical potential goes above the next level, we have the next level filled. We have this jump, jump, jump. Now, these are London levels E0, E1, E2. Whenever chemical potential goes above the next London level, this London level is filled. Sigma xy jumps in. This is what most people think about quantum physics. I talked to many. This quantization here has nothing to do with quantum physics. The actual quantum content is this part. And the difference is Fermi energy versus density. Quantum Hall effect is quantization of sigma xy as a function of density and not quantization as a function of chemical potential. I will make this as red as possible. Still like that, but this is not quantum Hall effect. If you see this plot here, this is not quantum Hall effect. Why is it important? To show you that it is important, I will need plot number 5. Just you look at these two plots, how the density of states and Fermi energy depend on. Let's try to guess what is the dependence of sigma xy on the density. So now we increase the density. We add electrons one by one to the system. What will happen? If I add the first electron, what happens?
I mean nothing.
No, I mean it will go to the first electron. Then you add the second electron. It also goes to the first electron. So when we increase the density of states here, what we do, we gradually fill the first one over. Chemical potential doesn't change. It stays just at this level. What happens with sigma xy? Sigma xy actually grows linear because each electron that you have added electron contributes the same contribution. If you fill one Landau level, all electrons are equivalent. And when it's filled, you have a jump. The chemical potential jumps to the next Landau level. Your Fermi energy jumps. Sigma xy doesn't change. But it's only 1 point, because when you add the next electron, it fills the next Landau level, and more electrons, they will gradually fill the second Landau level. It continues to grow bigger. So these points where you switch from one Landau level to the next one, at these points, chemical potential jumps, but density doesn't change, its xy doesn't change. So they're just invisible points in this straight line.
I don't think this is true. I think you can show by a geometric argument. Because like what I saw, like an argument where you, so let's say that you have a 2D torus or some this type of structure or this type of construction, and you, instead of like having a voltage, you consider a change in the magnetic field in this middle torus. And you still, even without this order, you can then by geometric argument.
You probably are talking about the argument with the Laughlin argument.
Loudly, yeah.
Laughlin. Let's discuss it later. Well, actually, that's a valid argument, but that's the correct one. But here I'm talking about just an infinite two-dimensional system which has translational symmetry. And this translational symmetry is important. Okay, so this is what should happen if you have an ideal system, very clean, with Landau levels, and you fill the electrons gradually one by one, you increase its concentration, sigma xy decreases linearly, there is no quantization. So, from these two things, from this one and from this one, you will conclude that of course sigma xy depends like this on the Fermi energy, but it's just because Fermi energy itself has jumps as a function of concentration. So if you compute Fermi energy from this graph and insert it here, the dependence sigma xy on n will be just linear. So on this plot, Fermi energy is constant, concentration grows. We go along this line, and in that plot we go along this vertical line. Sigma xy grows. Then at some point, the next electron we jump to the next Landau level in one step. And here we jump in one step to here, we continue the linear growth. So if we plot sigma as a function of n, it will be just a linear function, nothing else. And actually, there is another argument. If you take the simplest problem with parabolic spectrum, magnetic field, equidistant Landau levels, you can prove that sigma xy should be a linear function of n, because this is a consequence of the Galilean invariance. In the parabolic spectrum, you have Galilean invariance, you can go to a moving frame with a constant velocity and just only momentum shift. And then magnetic field should, this Lorentz force can be taken into account and go into a moving frame in its own direction, and it actually proves that each electron provides the same contribution with respect to its energy. It can be shown. It's quite.
So the statement is that the quantum Hall effect has nothing to do with
Quantum Hall effect has nothing to do with Landau levels and quantization of the space. Moreover, there is a very famous paper from the year 1988 written by now Nobel laureate Pavel with the name Quantum Hall effect without Landau levels. So, Landau levels have nothing to do with quantum Hall effect. Quantum Hall effect, of course, may exist in a system with Landau levels, but it might also exist in a system without any Landau levels. And vice versa, you can have Landau levels and have no quantum Hall effect. So, very last thing, we should finish somewhere here. So, why does quantum Hall effect actually occur? This is also a statement. A statement written in red, quantum for the fact, occurs or is equivalent or is a consequence of disorder. Only presence of disorder and localization is required to have quantum for the fact. If you consider just a clean system of Galilean invariants with Lambda levels, everything is ballistic, you will never encounter any quantum point. And so what disorder actually does to the density of states? You have this single delta function, many states of the same energy, and at disorder, the energies are a bit changed. So each Lambda level becomes some peak of a finite width like this. With the same area. The total number of states is the same, but it has some width, and this width actually is 1 over pi. So the distance between Lambda levels is the cyclic frequency, and the width is inverse. And not only we have the width, all the states inside actually get localized. This is the localization we were talking about. When you have many impurities, there are localization corrections, conductivity is suppressed, and in particular, each eigenstate which electron is localized by disorder has nothing to do with magnetic field, they're just localized. Yeah. And if they are localized, they do not participate in sigma xx, and they also do not participate in sigma xy. So you add electrons, and nothing changes. Both sigma xx and sigma xy remain constants. But in the middle of each Landau level, exactly the center, there is a very special state, which is not localized. And when this special state is filled when electron goes to that state, this is when you have a jump to the next quantized value, and then you proceed filling the localized states. So the steps, they occur due to localization and also due to a very specific and non-trivial effect, which tells us that in the middle of Lambda level there is a delocalized state, even in the presence of disorder. And the reason why there is a delocalized state is topology. And this is what was an argument about Martin, was the proof that the number of these delocalized states should be related to the total flux in a particular zone. Okay. So, next time we will discuss how topology interplays with localization, and how can we at least approximately prove that